1 minute. This whiteboard is unable to load. 1 minute. So first we'll study about Ampere's law. Ampere's law. So this Ampere's law, actually Ørsted discovered the existence of the magnetic field due to current flowing in a conductor. It is whenever you have a conductor in that current, if current is flowing, then he explained the magnetic field will be developed. That is what Ørsted discovered. Then after Ampere quantitatively derived a relationship between the current I and magnetic field B. This relationship between this current and as well as the magnetic field is called as a Ampere's law. Okay, the relation between the magnetic field and as well as the current carrying conductor, which is carrying a current I, the relationship between them I and B is known as what Ampere's law will call here. And according to Ampere's law, the line integral of magnetic field B along a closed curve is equals to mu naught times the net current I through the area bounded by the curve. That is what we call it as a Ampere's law here. That is what we have to derive here. So Ampere's law is nothing but surface integral of B dot dl b dot dl, which will be is equals to mu naught times I you have. So this is what we call it as Ampere's law. So this statement again, once again, we'll see here the statement. That is the line integral of magnetic field B. Here B is nothing but the magnetic field. The line integral of a magnetic field B along a closed curve is equals to mu naught times the net current I through the area bounded by the curve. That is what we represent in mathematically like this surface integral of B dot dl is equals to mu naught I. So this is what uh, the representation, mathematical representation of this Ampere's law. Okay, surface integral of B dot dl is equals to mu naught I here. And you know that mu naught is nothing but the permeability of a free space or air we are going to be called here. Yeah. Ampere's law is used in finding the magnetic field due to symmetrical current distribution. So the main thing what we are going to get from the Ampere's law is Ampere's law, it is used to find the magnetic field due to a symmetrical current distribution if you have. Okay. So now we'll see the derivation of this Ampere's law. So for this purpose, in order to derive this surface integral of B dot dl is equals to mu naught I. So here we will consider a long a straight current carrying conductor we are going to be considered, in which some current I is flowing in that one, and the current carrying conductor will be perpendicular to the page directed outwards we are going to take here. So for that purpose, we'll draw here, uh, we'll take a current carrying conductor as well as that will be perpendicular to this one. So here, so here, right. So here we consider a we'll take a what we call a conductor which is perpendicular to the page directed outwards. Okay. So here from the center here, in this direction, which is outward direction, and it is carrying a current of I, if you say. So this is the current carrying conductor, right? So this is current carrying conductor, current carrying conductor. So this is the center we have, which is represented O, and the radius of this will be R. Okay. So we have taken a point O. This is the point O as the center we have considered. And if we consider a circular path of radius R here, R is the radius of the circular path we have considered, then the magnetic induction B at point of the circular path. Okay, magnetic induction B at a point on the circular path. So here we'll take a point, here we consider a point P, right? So this will be, B will be in this direction we have P here. So this is the magnetic induction B at a point P on the circular path, and this actually, which is given by uh, B is equals to mu naught I by 2 pi R. So this actually we will get from the Biot-Savart law. Later on we'll see about the Biot-Savart law also. So this we'll get from the Biot-Savart's law. So Biot-Savart's law. What is Biot-Savart's law? All those we'll see later on. So B is equals to mu naught I by 2 pi R here. And I is nothing but the current which is flowing through this conductor, current carrying conductor. And B, whichever we have taken here, the direction of B will be along the tangent of a circular path. So as we have drawn here, it is along a tangent of circular path you are going to be have here. Okay, which is regarding B. So regarding B, you have to be remember 2 points here. One point about this B, which you have to remember is the magnitude of B is constant at all points on the circle. This point you have to remember. Okay, the magnitude, the magnitude of B, the magnitude of B, it is constant at all points on the circle. Is constant at all the points on the circle. This point you have to remember one thing about B, and another point you have to remember is this is parallel to the circuit element DL. This you have to remember. Okay, this is parallel to the circuit element. This is parallel to the circuit element DL. So here we have like a length is DL. These 2 points you have to remember. So therefore, the line integral of magnetic field B along the circular path is given by the line integral of magnetic field B along the circular path is given by surface integral of B dot dl. So which will be equals to surface integral of B dl cos 0. BDL cos 0 degrees. So which you are going to get it as a surface integral of BDL. So B is constant as we have mentioned. Surface integral of DL you are going to be have. And this is a parallel to the circuit element. So we have got a BDL cos 0. So therefore B is constant we have taken outside. Surface integral of DL is nothing but B into 2 pi r. Surface integral of dl is equals to p into 2 pi r. So we have written p 2 pi r. So uh, this actually the surface integral of dl, whichever we have written as a 2 pi r, that is the circumference of the circle actually we have written here. So we have got one thing is surface integral of b dot dl is equals to, we have got it as a b into 2 pi r we have got. So from the Biot-Savart we have b is equals to mu naught I by 2 pi r. And here we have got b dot dl is equals to as a b into 2 pi r we have got. So from these two equations, substituting the value of b from equation 1, whichever we have mu naught I by 2 pi r in this equation 2. So substituting the value of b from equation 1 in equation 2, if you substitute, okay, so we'll get it as a surface integral of b dot dl is equals to, in place of b, I'm writing it as a mu naught I by 2 pi r I'm writing, okay, into, you have already this dl is equals to, we have got it as a 2 pi r, so it will be 2 pi r here. So this 2 pi r and this 2 pi r will get cancels. We get it as a mu naught I. So that is nothing but the line integral of b dot dl. The line integral of b dot dl over a closed surface area. B dot dl is equal to, we have got it as what? Mu naught I here. Okay. So the surface integral of b dot dl is equal to mu naught I is nothing but the Ampere's law which we have. So this is what we call it as a Ampere's law. So this is a mathematical expression and we have derived the mathematical expression here. Okay. And next we will see about Biot-Savart law here. Next we'll see about Biot-Savart law. Next topic is We have a biot. So, okay, biot Savatla. So according to our Ørsted experiment, what actually tells is when a current carrying conductor produces magnetic field around that. Already we have seen that is whenever a conductor is there, in that conductor, if some amount of current is flowing, so automatically around normal it is going to be develop this magnetic field. So that is what uh, Ørsted experiment we have. So it is in year 1820, Bayat and Savart performed a series of experiments to study the magnetic field produced by various current carrying conductors. Okay. So what type of magnetic fields, that means how much, what is the magnitude of these magnetic fields? They have seen several experiments, and they have obtained a relation between this B, which can be calculated at any point of space around a conductor in which a current is passing. So the relation is called Bayat and Savart law. So these two scientists, Bayat and Savart, they have performed so many number of experiments to study the magnetic field produced by the various current carrying conductors, and they have given, otherwise they have related, otherwise they have obtained a relation between uh, B, which can be calculated at any point of space around a conductor in which a current is passing. That is what we call it as, the relation is called it as a Bayards and Savart law we are going to be called. So in order to get this Bayard Savart law, we will consider a conductor we are going to be consider of any arbitrary shape we are going to be take, in which some current I's should flow in that one, and we'll take a point P at any which is at certain distance from this what we call conductor, and we will calculate the magnetic field there here. Okay. So for that purpose, so here what we are doing is we are going to be consider a conductor. So we consider a conductor here, which is AB, we are going to be named here. So here, which is having any arbitrary shape, we are going to be called here. So this one is a conductor. Here we have taken of any arbitrary shape here. So in the AB is a conductor which we have named here. In this, the current which is flowing is I here. Okay. So we have taken a conductor AB of any arbitrary shape we have been taken here, and in which current I is flowing here. Now we consider a point P at any point at any some which is at a distance from the this what we call a conductor. So here we consider a point P here we consider. So here we will take a small amount of this conductor, which we call it as a, which is having a length of small length dl. Okay, dl, and this is at a distance from the point P. So this distance we will make it as r here. Okay. So what we have considered is, we have considered a conductor AB in which current I is flowing. We have considered a point P which is located at a distance of r from the conductor to a small element dl here. Okay, dl be the length of a small element here we have been considered. Okay, so according to Bayat and Savart, the uh, field B at any point can be computed by dividing the conductor into short current elements here. So the field distribution dB at that point due to each element is calculated the total field B is then resultant of the infinitesimal field of all the elements of the conductor. That means here the entire conductor, whichever we have been taken AB, it is going to be divided into smaller current elements. We are going to be divided, and then after we will be calculating the magnetic field due to a small element. We are going to be calculate. Then after we are going to sum all the magnetic fields for all these small elements, infinitesimally small elements. Then we are going to be get the total magnetic field due to this entire conductor. We are going to be get here. Okay, so now for that purpose, we have considered a small element dl. We have been considered here. So this is a dl is the small element whichever we have been taken. This is the length of one small such small element we have been taken, and this is at a distance of r um, from the point P we are going to be have. Okay. R now we consider R be the displacement vector from the point P we are going to be considered here. So Bayat and Savart observed that dB at that point P due to small element dl of a current carrying conductor depends upon the following factors. Okay, so we have considered a small element here dl we have been considered, which is located at a distance of r from the point P where we are calculating the magnetic field here. Okay, so this dB, whichever the magnetic field which is going to be have due to the small element dl, which is uh, dB is the magnetic field due to the small element dl at a point P, which is at a distance of r you are going to be have. So Bayat and Savard, they have observed that this small element dl of a current carrying conductor depends upon the certain factors. Okay, it is going to depends upon the certain factors. What are those factors? Is first factor which is going to be have here. It is first one. Uh, Actually, it is directly proportional to the current I flowing through the conductor. That is nothing but dB here we are calling. So dB is directly proportional to the current I which is flowing through the conductor here. So dB is directly proportional to the current flowing in the conductor small element. Okay. So then after one more point here we have is it is directly proportional to the length dl of the element which we have been considered. So here dB is also directly proportional to the length of that current carrying conductor. This is also one point we can observe. And another one is it is directly proportional to the sine of the angle theta here. It is directly proportional to the sine of the angle theta between the length of the element and the line joining the element of the point P. Okay, so this is the length of this element and this is the line joining this point P here. Okay, so this dB is directly proportional to the sine of that angle, sine theta we are going to be called. And then after fourth point, which we have to remember here, it is proportional to the square of the distance r of the point P from the element dl. Okay, it is inversely proportional, sorry, it is inversely proportional to the square of the distance r of the point P from the element dl. That is nothing but dB is inversely proportional to the square of the distance here. Okay. So Bayat and Sawatla, what they have observed is here initially again, once again, I'll explain here. They have considered a current carrying conductor AB of any arbitrary shape, and that AB current carrying conductor, it has been divided into smaller elements. So number of elements it has been divided. One such element is a DL. Here we have taken a small element current carrying conductor DL we have taken, and we have a point P where we have to calculate the magnetic field developed by this conductor that we have been called it as a dB here. So therefore, this small due to the small element of a current carrying conductor, um, dB, whichever it is going to develop, it is going to be depends upon the factors. So this dB, whichever it is it is directly proportional to the current carrying conductor current I, which we have written it as a dB is proportional to I here one point. And then after this magnetic field, whichever it has been developed, dB, is directly proportional to the length of this small element dl. So dB is directly proportional to dl, one point. And third point which we have is this dB is proportional to the sine of the angle theta between the length of the element and line joining the element to the point P. So that is what we have represented. dB is proportional to sine theta. One more we have. And then after, one more point we have is this dB is inversely proportional to the square of the distance r of the point P from the element dl. So therefore dB is directly proportional to 1 by r square we have. Now we have we have dB is proportional to I, dB is proportional to dl, dB is proportional to sine theta, and dB is proportional to 1 by r square. So now we will combine these four so that we'll get equation. Now we will be combining all the factors. Okay, combining all the factors, all the factors. So therefore, what we are going to get is dB is proportional to I dl sine theta by ideal sine theta by r square we have. dB is proportional to ideal sine theta by r square here. When now after this, when the conductor is placed in a vacuum or air, suppose if the conductor is placed in a vacuum or air, so this becomes dB is equals to, it becomes it as a mu naught by 4 pi into ideal sine theta by r square you'll get. Okay. So when we have taken this conductor which is placed in a vacuum or air, if you consider, then we'll get a dV is equals to mu naught by 4 pi ideal sine theta by r square you are going to be get here. Okay. So this mu naught by 4 pi is proportionality constant. Here we have this mu naught by 4 pi is nothing but mu naught by 4 pi. This is nothing but the proportionality constant. This is proportionality constant we have. And you know that this mu naught is nothing but the permeability of the free space. Mu naught is the permeability of the free space. Permeability of the free space we have. Now this, if you represent in a vector form, the same in a vector form, we can write it as, in a vector form, we can write this as dB is equals to mu naught by 4 pi into I dl r cap by r cube. Okay, this is the in a vector form we have. So from Bayard-Savart law, what we have seen is the field, magnetic field, which is developed due to a small element dl is given by dB, and this dB is actually directly proportional to the current carrying in that conductor I, and this dB is directly proportional to the length of that current carrying conductor dl, and also this dB is proportional to the sine of the angle theta, which is present between the length of the element and line joining the element. That is dB is proportional to sine theta, and also dB is inversely proportional to square of the distance between the point P and to that conductor. Okay, so from that we have got our dB is equals to mu naught by 4 pi into ideal sine theta by r square. That can be represented in the form of vector form as mu naught by 4 pi ideal r cap by r cube here. So here r cap is nothing but the unit vector in the direction of the line drawn from the current DL to the point of observation P. This is known as a position vector we are going to be called here. Okay. So the resultant field at P can be obtained. Okay, the resultant field. So this dB is nothing but what actually this is the field due to a small element dl. So dB is nothing but this is the field produced due to small element dl, small element dl here. Suppose if you want to calculate the magnetic field due to the entire current carrying conductor at that point P. If you want to get, then simply what we have to do is we will get it as a B is equals to surface integral of integration of dB we are going to be get here. B is nothing but the integration of dB we are going to be get. Okay, so um, if you do the integration of this dB, we are going to get that one. So this is what we have the what we call Bayard-Savart law we have. Okay. So this dB is equals to mu naught by 4 pi into ideal r by r cube in a vector form we have this one. Okay. So this is what the Bayard-Savart law. Next, we will calculate the magnetic field due to a long straight conductor carrying current we'll see here. Next topic is a magnetic field. Magnetic field due to long straight conductor. Due to long straight conductor which is carrying a current, which is carrying a current. Right. So this magnetic field due to long straight conductor which is carrying current we have to see here. So we'll consider an infinitely long conductor we have to consider, which is placed in a vacuum and which is carrying a current I we have to take. And for that purpose, we'll consider that one. So here, small part we consider here. Right. So here angle between them is theta. Yeah. So this is O. This one is a DL, a small element. Yeah. So this distance will be, again, we have different. This is the length L we consider. Okay. So the distance between this O2 P is, we consider it as a R, capital R we are going to be consider. And this is the magnetic field which is going to develop is dB. This is the another distance R. Okay. So in this, the current flowing is I here. Okay. So we have considered a long straight conductor we have been taken and which is placed in a vacuum and which is carrying a current I is shown here in this figure here. So now the aim is to derive an expression for magnetic induction V due to the conductor at a point P on the x-axis. So this is the x-axis which we have on this x-axis. We have to derive the magnetic field induction. We have to derive here. Okay, we have to derive on the x-axis, which is at a point P, which is located on the x-axis, which is at a distance of r here. Okay, so the distance between O and P uh, is r you are going to be have. And O is nothing but this is the foot of the perpendicular from the point P to the conductor we have. So we considered a small element AB here. We have been considered a small element of length DL here. This is the small element of length DL, which is AB we have been considered. Okay, of conductor. A distance of L here, a distance of L from the from O you are going to be have. Now let R be the distance of the element from the point P here. Okay, this one. R is the distance of the point P from that small element DL. So now we have taken this theta. This theta be the angle in clockwise direction, in this clockwise direction to the element uh, joining the element to point P here. The magnitude of the field dB due to the element AB at a point P is given by. So due to the small element DL at the point P, the magnitude is given by. Already we have derived the in the Biot-Savart, which is a dB is equals to mu naught by 4 pi into IDL sine theta by r square we have. So this is already we have derived. So from Biot-Savart for any arbitrary shape of conductor, if a point P is located at a certain distance, the magnetic field due to the small element is given by dP is equals to mu naught by 4 pi into IDL sine theta by r square. Now the field due to the whole conductor we want to calculate here. The the field due to whole conductor. That is for a small element. This dB is the magnetic field you have. So for an entire conductor, that is a whole conductor. Due to this whole conductor, what is the field we have to calculate, which is given by the field due to the whole conductor is given by, this is nothing but B actually we call. So this is nothing but integration of dB you are going to be have. So here integration of dB is nothing but mu naught by 4 pi into IDL sine theta by r square you have. Okay. So in this equation, mu naught by 4 pi is nothing but which is a constant actually. Mu naught by 4 pi is constant. So therefore we can write B is equals to, if you take mu naught by 4 pi is constant, we can take outside. So it is integration of uh, I is also constant, which is flowing through that conductor, current which is flowing through that conductor. So it will be sine theta dl by r square. As we have taken this is a long straight conductor, so its limits from minus infinite to plus infinite you are going to be have. It is in between the limits from minus infinite to plus infinite we have to consider here. So now for the magnetic field B due to the entire or whole conductor is given by integration of dB, which is equals to mu naught I by 4 pi in integration in between the limits minus infinite to plus infinite sine theta dl by r square we have got. So now from this figure, we can take the value of r here because it is a right angle triangle here we have. So from the from the figure, R is equals to, you are going to get it as L square plus R square whole to the power of half. From the right angle triangle, R square is equal to L square plus R square, you are going to be half. R is equal to root of this. That is nothing but L square plus R square whole to the power of 1 by 2. And if you take the sine theta value, that angle which is making, so sine theta, we can write it as sine 180 minus theta, we can write, because sine 180 minus theta is same as it is sine theta. So which will be equals to actually uh, capital R by small r, you are going to be have. So therefore, sine theta is equals to, sine theta is equals to capital R, and small r we have got it as L square plus R square whole to the power of half. So that is L square plus R square whole to the power of half we have. Okay. So now these substituting the value of R and sine theta in this equation, if you substitute, so substituting the value of R and sine theta in equation 2 here. So if you substitute, what is the equation 2 have is B is equals to, we have mu naught I by 4 pi we have. So integration in between the limits minus infinite to plus infinite. Sine theta place, we have, in place of sine theta, we have R by R square plus R square whole to the power of half. So it will be R by L square plus R square whole to the power of half into DL we have. This is take the question number 3 here. So now what we have to do is, in order to evaluate this integral, we will substitute the values. This integral we have to evaluate. So this integral we have to evaluate. So in order to evaluate this integral, what we'll do is we will substitute in place of L is equals to R tan alpha, and DL is equals to, we'll get R is secant square alpha d alpha. Okay. So here, in order to evaluate, in order to evaluate, in order to evaluate, we substitute, in order to evaluate integral actually, in order to evaluate integral, we substitute, L is equals to R tan alpha, we are going to be substitute. So therefore, if you do the differentiation, we'll get DL is equals to R secant square alpha d alpha, you're going to get. And the limits are going to be in between minus pi by 2, pi by 2. Limits also, limits will change minus pi by 2 to plus pi by 2, it is going to change. So therefore, B is going to be, mu naught I by 4 pi integration in between the limits minus pi by 2 plus pi by 2, it is going to be changes. And we have R already is there. In place of dl, we have R into secant square alpha into d alpha. So R into secant square alpha into d alpha. In place of dl, we have substituted R into secant square alpha d alpha, divided by, we have L square plus R square. So L square is nothing but, L is nothing but R tan alpha. L square is R square tan square alpha plus R square. R square as it is, we are going to be right, whole to the power of 1 by 2 you have. Okay. So 1 by 2 means it becomes, sorry, it becomes 3 by 2. Actually, here also we have, mistaken. So it should be L to the power of 3 by 2. Already 1 by 2 is there. It should be 3 by 2. Therefore, we have got this one. So from this, uh, if you continue, so we will get it as a mu naught I by 4 pi, limits from minus pi by 2 to plus pi by 2. So you get it as a um, r square secant r square secant square alpha d alpha divided by, so if you take a r square r cube outside, so inside you have a 1 plus tan square alpha, 1 plus tan square alpha into whole to the power of 3 by 2. So from this, you'll get it as a mu naught I by 4 pi integration from minus pi by 2 plus pi by 2. So this 1 plus tan square alpha is nothing but secant square. And here it remains with the d alpha by r secant alpha you are going to be have secant alpha. So therefore it will be mu naught I by 4 pi integration between the limits minus pi by 2 to plus pi by 2. That will be 1 by secant is nothing but cos alpha. Cos alpha d alpha. This r also, if you take outside, it will becomes mu naught I by r in 4 pi r it becomes. So therefore, this will be mu naught I by 4 pi r, and the integration of cos alpha is sin alpha, and the limits are from minus pi by 2 to plus pi by 2. So therefore, will be mu naught I by 4 pi r into, so it will be limits, if you substitute, it will be 1 plus 1. Okay, sin 90 minus half minus plus, it becomes 1 plus 1. So it will be b is equals to mu naught I by 2 pi r, it becomes mu naught I by 2 pi r. So the units for these are Weber per meter square. So this is nothing but the magnetic field due to a long straight conductor which is carrying a current I here. So this is what we have. Okay. So this is the expression for the magnetic field due to induction near a long straight conductor. Okay. So if the lines of magnetic induction around the straight conductor carrying a conductor, you can calculate from this same expression also. So in the today's class, we have seen about like Ampere's law as well as the Biot-Savart's law, and application we have seen. So if you see about Biot-Savart law, so we have considered a current carrying conductor of any shape, arbitrary shape, which is carrying a current I. So we have to calculate what is the magnetic field due to this current carrying conductor at a point P, which is located at a distance of r from the small element dl. So why we have taken the small element means we have been divided into smaller elements dl. So we have taken a point P, which is at a distance of r. And from that Pyatt and Savart, they have given certain points. This magnetic field due to a small element dl, which is proportional to the I and which is proportional to dl and also proportional to the sine theta, that is angle made by this, and it is inversely proportional 1 by r square. It is inversely proportional to r square. So by combining all these, we get that dV is equal to ideal sine theta by r square we are going to get. So if you remove this proportionality, we get it as a mu naught by 4 pi. So this dV is equals to mu naught by 4 pi into ideal sine theta by r square we have got. Okay. So this is what about Savart law we have. So then after we have like Ampere's law. Ampere's law is nothing but we have calculated uh, current which is on a circular path. So we have taken a current carrying conductor I, which is normal to the surface. This is a closed surface here. So which is having a radius of r we have taken. So from the Biot-Savart law, we have taken B is equals to mu naught I by 2 pi r we have taken. And 2 points which we have to remember is this, the magnitude of B is constant at all points on the circle we have to remember. And one more thing is this dB is parallel to this circuit element dl. So this surface integral of B dot dl is equals to surface integral of B dl cos t 0 actually, that is parallel. So therefore it will become surface integral of B dl. So B is constant we have taken outside. So B into surface integral of dl. So which is equals to 2 pi r. So we have got B 2 pi r. So this value we will be substituting in this equation 1. So that we have got mu naught by 2 pi r into 2 pi r. So it will becomes mu naught I. So that is nothing but Ampere's law is the line integral of a magnetic field B along a closed curve is equals to mu naught times the current carrying in that one. Current carrying through the area bounded by the curve. So that is the surface integral of B dot dl is equals to mu naught I we have got. So this is what Ampere's law we have seen, and also Biot-Savart law we have seen. And then after, the magnetic field due to a long straight current carrying conductor we have taken. So for that purpose, we have taken a current carrying conductor, and with on the x-axis a point P we have been taken, where we have to calculate this B we have to calculate. So for that purpose, we have taken a small element. So due to that small element, the field uh, due to the small element dB is given by mu naught by 4 pi into ideal sin theta by r square. It has been given, and we have to calculate the field due to the whole conductor. So we have to integrate. So if you integrate this in between the limits minus infinite to plus infinite, we have got it as a mu naught I by 4 pi sir, integration minus infinite to plus infinite sin theta dl by r square we have got. So from this figure, we have calculated the r value from the right angle triangle, and also sin theta we have calculated. So the value of r, small r, and as well as sin theta we substituted there, and we have got B value is this one. So if you calculate, we have got B is equals to mu naught I by 4 pi r into sin alpha between the limits minus pi by 2 to pi by 2. So before that, we have to, in order to evaluate the integral, we have taken L is equals to r tan alpha we have taken. So from that, becomes r into secant square alpha d alpha. So these values, if you substitute, we have getting it as a mu naught I by 4 pi r into 2 we have getting. So that we have got it as a B is equals to mu naught I by 2 pi r. So this is what the magnetic field due to long straight conductor which is carrying a current I. So this is these are the three topics which we have. Okay. So in the next class, we'll see some more. So we'll stop here.